Let's do another example, this time using a deforming control volume. This is a little complicated problem in which an L-shaped tube of constant area A is filled completely with water and is held as shown. There is a plug at the lower end which is holding this water like this. The pressure increases hydrostatically down the vertical leg and is constant throughout the horizontal leg. Then, at time t is equal to 0, we remove the stopper at the lower right end and the water starts to drain out. The gauge pressure at the exit becomes 0 when the water starts draining out. We cannot use one control volume throughout this volume, because if we use one control volume, there would be horizontal forces and vertical forces in each one of them. Instead, we break this volume into two, control volume 1 and control volume 2. The pressure throughout the vertical leg is in the x direction, horizontal on the curved wall, except at the two ends, the top and the bottom end. The pressure on the cylindrical part of the control surface would not affect the vertical momentum equation, the Z momentum equation, because those forces are horizontal. Similarly, the pressure distribution throughout the horizontal leg, that is the cylindrical part of the control surface of control volume number 2, is not in the x direction and would not enter the x momentum equation. So, we will write the Z momentum equation for control volume 1 and the x momentum equation for the control volume 2. For control volume 1, we have shown the forces. There are two forces. One is the weight of the fluid within the control volume, and the other is the pressure force acting upward on the surface at the lower end of this control volume. When the level of fluid is changing at a rate h dot, the fluid volume within both the vertical and horizontal leg is moving with the speed v is equal to h dot. If dh by dt is the rate at which the level is falling, h dot considered positive upward, then the velocity is h dot. Here the h dot would be negative, so velocity would be negative. The Z momentum contained within this control volume number 1, at time t is rho ah, the mass times h dot, the velocity. Mass rho ah times the velocity h dot. This is the momentum at time t. So, what is the rate of accumulation? Rate of change of this momentum, del by del t of rho a h h dot, which is shown as rho a into h plus h double dot plus h square. In this deforming control volume, there is no flux of momentum at the upper end, but the flux at the lower end is minus rho h dot times h dot. Minus rho a h dot is the volume coming out is negative because it is downwards times h dot, and so the net efflux of momentum is minus rho a h dot square. Putting the two together, we get pressure 1 gauge is rho gh plus rho h h double dot. Rho gh is purely the hydrostatic pressure and to this is added a pressure rho h h double dot, the acceleration of the level h, since h double dot is negative. So this is negative. Similarly, we work on the second control volume, the horizontal leg. Here, it is easy to see that the momentum in flux is the same as momentum of flux. Same volume, same rate the mass is coming in, same rate the mass is leaving. The velocity at inlet is the same as velocity at outlet. So net efflux is 0. Also, we evaluate the accumulation term. Accumulation, the total mass contained within this tube is constant at rho a times L2, but the velocity is changing, and the velocity is minus h dot. And so the rate of accumulation is minus rho a L2 into h double dot, because del by del t of the momentum contained within the control volume. And the momentum contained within the control volume is rho a L2, the mass, times the velocity, and the velocity is minus h dot. So this is the rate of accumulation, and that should be equal to the net external force applied on the system. And the only external force in the x direction is P2g times A. And from this, we get P2g is equal to minus rho L2 h double dot. Now what next? The next is, if the volume of the bed is very small, the pressure P1 should be equal to the pressure P2. And we equate the two to obtain this equation. And this equation is simplified to obtain h double dot is equal to minus gh divided by h plus L2. The problem is solved. This tells you the rate at which the level would fall and the acceleration of that level. Let's do one more example. In this example, we try to find out the pressure loss in a sudden expansion. We discussed in an earlier lecture that as a liquid flows in a pipeline with a sudden expansion of the diameter of the pipe, then the flow separates at these locations, and the eddy is trapped in this dead water region, an annular dead water region. The flow comes out, the velocity remains the same as here, and this flow then reattaches quite a ways downstream. We have shortened the distance in this picture. For illustrating it, we have to find out what is the pressure difference between section AA and section BB. Let's take a control volume like this. We draw the picture of this control volume and the forces. Because the velocity does not change at location A, the pressure all across at section AA would be P1, and all across section BB would be P2. So we can calculate the net horizontal force as P1A minus P2A in the horizontal direction. And that should be equal to the net efflux of momentum. The influx of momentum at AA is rho V1A1 influx into V1, the velocity at V1. The efflux of momentum at BB is rho V2A2 minus V2. The net external force P1A2 minus P2A2 is equal to net efflux. So efflux at BB, which is rho V2A2 into V2, plus the efflux at AA. But the efflux at AA is negative of the influx at AA. So it is minus rho V1A1, the mass flux times the velocity V1. The mass balance equation permits relating V2 with V1 as V2 is equal to A1 V1 divided by A2. And we use this in the above equation. We get P2 minus P1 divided by rho V1 square is equal to A1 divided by A2 into 1 minus A1 divided by A2. Up till now, in all calculations of momentum efflux, we have assumed the flow to be uniform across the inlet and the outlet. At 1, the velocity is 1. At 2, the velocity is 2. But usually in controlled volumes, the liquid or the fluid enters through a pipe. And we know very well that there is a velocity profiles across this pipe. If the flow is laminar, fully developed, the profile is parabolic. If it is turbulent, it's most likely to be a 1/7 power law. We can still work with the one-dimensional assumption, but with a momentum correction factor. We define a momentum correction factor beta, just like we defined an energy correction factor gamma when we are dealing with the energy equation. So we define beta is equal to actual momentum flux divided by momentum flux when the same mass crosses at the average velocity, which we have been doing so far. So the actual momentum flux would be the integral over the whole area of rho V square dA, rho V dA times V, integral of that. And the momentum flux when the whole mass crosses at V average is rho V square average times A, where V average is equal to 1 over A integral over area of V dA. We have done that before. So this correction factor can be evaluated by evaluating the integrals. For a circular port of radius r, capital R, the velocity is a function of the radius r alone. So consider a ring of thickness dr at radius small r, and the total momentum flux would be twice pi rho integral 0 to capital R, r V square dr. This is the numerator, and the denominator would be simply rho times the area pi r square into V average squared. That is, beta is equal to the numerator divided by the denominator. Now, we evaluate this factor beta for laminar flow first. For laminar flow, the velocity profile is parabolic. that is V is equal to V max into 1 minus R star square. And the V average we have shown before is 1/2 V max. So that V over V average is twice into 1 minus R star square. The above integration yields beta is equal to 1.33. If we had used a turbulent flow, a very common profile is the 1/7 power law profile of the form V is equal to V max into 1 minus R star raised to power 1/7. And with this profile, we can obtain V average as 0.817 V max. This we did when we were evaluating the energy correction factor. So that the V over V average is given by 0.817 into 1 minus R star raised to power 1/7. And the integration integrated above gives beta is equal to 1.020. A very small correction over 1. So, if the flow at the inlet or the outlet or at both locations is turbulent, as it is more likely to be since most economical flows are turbulent, we may not apply momentum correction factor because this will result in an improvement only by 2%, not significant.